let's review the graphs of polynomial functions so far. So on the left there, we will look at the linear function y equals mx plus b, where m equals 0. So the slope in this case is 0. And I'm sure you'll all know what that line would look like. That will be a horizontal line that would pass through the y-axis at some point, and the slope is 0. Now, because the slope is 0, the equation just simplifies to y equals b, where of course b is that y-intercept. So this would be our point B right here. And this is still a polynomial function. It's the simplest type possible. And technically speaking, you could think of the degree of this one as degree 0. And you might wonder why that would be a degree 0 function. And that's because if we were to write b with the variable x, the exponent on that x would have to be 0. As we all know, x to the 0 is equal to 1. So we get back to just simply a horizontal graph going through the y-intercept of b. So that's basically your most simplest type of a polynomial function at degree 0, 1. Now when the slope isn't 0, you could have two cases. You could have a positive slope and you could have a negative slope. So let's draw one of each here. So there's a positive sloping line, and we'll draw a negative sloping line. Now, because the slope is not 0 in these cases, we would have a first degree polynomial function because there must be an x term within the equation, and the exponent on that x term would indeed be simply 1. Now let's give these two lines sample equations. And these are just sketches, so we don't really have a scale here. So let's call this positive sloping line y equals 3/4 x plus 1. And let's call the negative sloping line y equals negative 3/2 x plus 4 perhaps. Now what I'd like to focus in on here is the leading coefficient for both of these equations. So for the positive sloping line, we've agreed that the degree is 1 and that the leading coefficient in this case would be the 3/4. In our negative sloping line, then again degree 1, the leading coefficient would be this negative 3/2. And in the last activity, I think you started to look at end behavior of linear and quadratic functions. So let's just quickly examine that. Now before we actually talk about end behavior, let's just make sure we refresh our memory on the quadrants on a Cartesian plane. So this is quadrant 1. That's where the x is positive and y is positive in our ordered pairs of points. Quadrant 2 would be this quadrant, and we continue counterclockwise around to get the other quadrants. And what you'll notice then, if we go back to our graph with the two lines on it, is that we can now talk about where the line begins in what quadrant and where it ends. And for the positive sloping line, it starts in quadrant 3 and finishes up in quadrant 1. We're looking left to right, obviously, as we look at this graph. Just the way you'd read a book from left to right, we'll read a graph from left to right. With the negative sloping line, it starts in quadrant 2 and finishes up in quadrant 4. And what this allows us to do now is talk about the end behavior of polynomial functions here. And with the positive sloping line then, we have a case that as x gets really large negative, in other words, if we go this direction here, the line goes very large negative in the y direction. And we would write that as x approaches negative infinity, the y values also approach negative infinity. At the other end of the line, as the x values get very large, so as x approaches positive infinity, we'll notice that the y values also approach positive infinity. So what we're saying here is a degree 1 polynomial function with a positive leading coefficient will start in quadrant 3 and finish in quadrant 1. Or more mathematically, as x approaches negative infinity, the y values approach negative infinity. And as x approaches positive infinity, the y values also approach positive infinity. So just to wrap up the negative sloping line, you can see it's starting in quadrant 2 and finishing in quadrant 4. So we have a case that as x approaches negative infinity here with a negative sloping line, the y values actually approach positive infinity. And as the x values get really large, that is, they approach positive infinity, the y values approach negative infinity. And this will be important notation as we start to classify quadratics next, and then cubics and quartics and quintic functions, and really looking at leading coefficients and the degrees of these polynomial functions.